Good afternoon to all. Welcome to the ninth week tutorial session of NPTEL course, Convective Heat Transfer. My name is Ananthakrishnan. I'm a Ph.D candidate from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. So in this week, we will see a few numerical problems and multiple choice question based on the ninth week lectures. So basically, those contents are based on natural convection through duct, maybe enclosures, internal natural convection, partially divided enclosures, inclined enclosures, and so that completes the internal natural convection portion, and then we will move to the turbulence section where we will see a few one or two questions, numerical questions based on the starting of turbulence scaling analysis principle. Then if you have any doubts, you can post them on the course website. There is a forum available, and we will try to answer them as and when we could. Without wasting much time, we could go to the problem straight away. Look into the first problem. This is internal natural convection problem. Look into it, and I'll also try to solve it within a couple of minutes. The question states that machined into a solid ball of temperature T is a slender two-dimensional cavity of height h and length L, such that height is very much less than horizontal dimension L. The cavity communicates laterally with an infinitely large fluid reservoir of temperature T plus delta T. So the bottom and the top wall is at T cold, and then there is a fluid which is at the warm T warm, and so the solid wall is at the temperature T, and the reservoir is at a temperature T plus delta T. So if you assume this T cold will be T and T warm will be T plus delta T, we need to show that if a cavity is slender enough, that is, this dimension is very much higher than this dimension, the buoyancy driven flow will penetrate the cavity only to a certain depth whose order of magnitude is given by this formula. So this requires a bit of scaling analysis where we need to show that this particular formula is satisfied for the buoyancy driven flow. So in this case, the certain depth whose order of magnitude is Lx is equal to h raised to h into Rah raised to 1 by 2. We need to prove that the we need to prove that the length of the buoyancy driven flow will only be Lx and it will not take the entire length. So we can try to solve this. So it requires scaling analysis and we need to prove that this formula is satisfied. So what we do is that we'll start from the basic governing equations. So the conservation of mass continuity equation is given as dou v by dou x plus dou v by dou y is equal to 0. Then momentum equation. So momentum equation in a different form we can write where is equal to in terms of strain function we could write where u is equal to minus of dou psi by dou y and v is equal to dou psi by dou x. This is a this is a combined form of the momentum equation wherein we wherein we uh, eliminate the term of pressure. So we combine both the x and y momentum equation in order to and we use this function to represent the derivatives of u and v combined together. And then energy equation will be u dou t by dou x plus v dou t by dou y equal to alpha dou square t divided by dou x square plus dou square t divided by dou y square. So we draw the schematic again, it will be like this is vertical and the natural convection will occur only for a length Lx and this portion will be stagnant and this height will be h. And this is y direction, v velocity, and this is x direction and u velocity. And this will be a t cold, and this will be t plus delta t. Total length is L. So this is a slender probe domain. So that means that L is here Lx is very much greater than h. So this when we substitute in this energy equation, we can determine the significant terms from the scaling analysis. So x will be scaled according to Lx and y will be scaled according to h. Therefore, we can ignore we can actually ignore the so u could be represented as minus of dou psi by dou y, and v can be represented as dou psi by dou x. So in that case, the first and second term will be scaled similarly. So the scaling will become psi into delta t divided by delta x into delta y. That could be scaled as h into Lx. So scaling the energy equation we get psi into delta t is the first term will be A will be scaled as this one, and on the right hand side, since h is greater than h is very much less than c, only the second term persists. So c will become alpha into delta t divided by x squared. So the scaling analysis will be between psi delta t divided by h Lx, so of the order of alpha delta t divided by x squared. So you can denote it by equation 1. So that is a scaling based on the energy equation. So now moving to the momentum equation, we can do the similar kind of a scaling for the momentum as well. So this could be represented as so epsilon will be represented as dou square psi divided by dou x square plus dou square psi divided by dou y square. And the term on the left hand side, based on the scaling analysis, can be reduced as so if you take the so what we could write is that u can be written as dou psi by dou y, and v can be written as dou psi by dou x. So both the terms will reduce to uh, psi squared divided by uh, A, B, C, and D. A reduced to so this particular term epsilon will be represented by these two terms, and here it since H is very much less than that of Lx, this term doesn't exist because this will be very much less compared to that of the second term. So only this term remains. So that will give us psi. This will be psi divided by h squared, and on the outside there will be psi divided by h into L. So it will turn out to be psi divided by h into uh, h cube into L. H cube into L. The B term will become, so if I, so U into dou epsilon divided by dou x can become, so epsilon can be scaled as psi divided by h squared uh, plus psi divided by L squared based on this equation. So since L is very much greater than Lx, so since this Lx is very much greater than S, so this will, the scale, the term which dominate is psi divided by h squared. Substituting it back, U will be dou psi by dou y. Y will be in terms of h and x will be in terms of L. It will become psi combined together. It will be psi squared divided by h cube into L. Similarly, the B term, this term will become the friction viscous term, nu into dou squares epsilon divided by dou x squared, and and similarly y is scaled in terms of x and x is scaled in terms of Lx. This is very, x is very high, x dimension, x scale is very much higher than that of y. So this is negligible compared to this, and hence only this remains. And epsilon can be scaled as similarly here, psi divided by h squared. So it will be psi divided by h squared, and similarly another h squared and mu. So it will be scaled as mu psi divided by h raised to 4. And the last term, it will be c. This will be c, and the d term will be bg dou t by dou x. So beta g delta t divided by x can be scaled in terms of Lx. So from these two, what we could see is that this is nu psi divided by h raised to 4, and this is L. Since L is very much greater than that of very much greater than x, we could assume that this is negligible compared to this, and hence what we could assume is that the scaling analysis will take of the form nu psi divided by h raised to 4 is of the order of bg delta t divided by Lx. So what we could see from equation 1 and equation 2 is that psi is an unknown. Uh, that's a string function. So if we can eliminate psi from both of them, we can have a relationship between the beta g delta t Lx and alpha term. Basically, we can get a relationship in the form of Rayleigh number. So equating 1 and 2, what we could say is that we can eliminate psi and we'll get Lx by h is of the order of Rayleigh number raised to 1 by 2, where Rayleigh number is given by g beta h cube delta t divided by alpha nu. So what we do is that we just divide this by this, and we can combine them together, and we can reduce the terms in the form of Rayleigh number, and thereby we get the scaling analysis function LH by H is also of the order of RH raised to 1 by 2. So this is what the question says. We have to identify in the case of this slender horizontal enclosure, there will be a stagnant section where even though there is a temperature gradient where the natural convection doesn't occur, natural convection occurs since it is open to a fluid of large reservoir, this section that is far away from the reservoir will not be participating in the uh, convection flow. With that, we can move into a second problem. It's a similar problem compared to the previous question, and its characteristics is very much similar to that of the first problem. Look into it. Meanwhile, I'll also try to solve it within a couple of minutes. So this question is similar to that of the first question, apart from the fact that this is a vertical wall. Uh, so in the previous case, it was a horizontal wall. Here, the bottom section of the wall opens to a reservoir. So the question says, consider the penetration of natural convection into a vertical slender cavity of height h and gap thickness L. H is very much greater than L, as is shown in figure. One end of the cavity is closed and the other communicates with a very large fluid reservoir. Rely on the scaling arguments to show that when a temperature difference delta T is established between the fluid reservoir and the wall, the flow penetrates vertically to the depth that scales as Ly is of the order of L into Rayleigh number based on L. Here, this is the fluid reservoir, which is at a higher temperature T plus delta T, and the walls are at temperature T. The total height is L, and the height up to which the natural convection the signals will be relayed is Ly. So we need to show that the Ly can be scaled according to L into RAL. So this follows similar analysis as out of the previous case. So in this case, we write the continuity equation again, just like the previous case. All the governing equations. Combine momentum equations. Dou eta by dou y mu dou square eta by dou x square plus dou square eta by dou y square plus b3 delta t divided by dx. So this is x direction and this is y direction b. And then the energy equation will be similar as at the previous case, where that will be u dot t by dou x plus v dot t by dou y equal to alpha dou square p divided by dou x square plus dou square p divided by dou y square. So here epsilon is equal to dou square psi by dou x square plus dou square psi by dou y square. Just like the previous case, u is equal to minus dou psi by dou y, v is equal to minus dou psi by dou x. So g acts in this direction. This is a vertical direction. So we can approach it similar in a similar manner. Compare. We can approach it in a similar manner compared to that of the previous question. Uh, what we do is that we use the momentum equation and perform scaling analysis. And just like the previous case, we will get a final equation when we equate. Uh, so just similar to the previous case, the left-hand side inertia term will be very much less compared to that of the friction and the buoyancy term. So it will be basically an equivalence between friction and the buoyancy term, and we have to see which out of this x or y is larger. Here x dimension is less compared to y dimension. Therefore, the y dimension, this particular derivative is negligible compared to this. So we can scale it accordingly. X will be scaled based on L, this horizontal dimension. So it will be scaled as so it could be scaled as nu. The first term will be scaled as epsilon could be scaled as uh, psi divided by L. There are two terms can be dou square psi divided by L squared and psi divided by h squared. H is very much higher than L, therefore only L remains. So it will be can be psi divided by L squared, and the other term horizontal dimension another L squared will remain. So it will be psi nu psi divided by L raised to 4. that will be and then that will be scaled to buoyancy term, that is G beta delta T divided by L. So this combined together, this will be the first equation, which will be giving the scaling analysis for this case, for the vertical, for the momentum equation. Similar to that previous case, we need to have the scaling analysis for the energy equation. Scaling analysis is very straightforward. X dimension is very less compared to Y, so this is bigger compared to this. But U, there will be U that could be represented as dou psi by dou X, and V could be represented as dou psi by dou Y. So basically, both of them will be having the same dimension. And here on the right hand side, X dimension is smaller compared to Y, so this term gets this is neglected compared to this, and hence we can write it as psi delta T divided by there will be one X dimension and one Y dimension. So L H and so I beg your pardon, it will not be L H, it will be L Y. So we have to prove that it won't be reaching the entire dimension of the L convection term, entire dimension of H, sorry. And the right hand side will be alpha delta T divided by L squared, a diffusion term. So comparing 1 and 2, we can eliminate psi. 1 and 2 eliminate psi. We'll get the scale for this case. So we'll get Ly is of the order of L into Rayleigh number of L, where Rayleigh number is equal to GB delta T LQ divided by mu alpha. So that is the scaling analysis that we have done for continuity, momentum, for momentum equation, for combined momentum equation and energy equation. And from that, we obtained the scale of the length up to which the natural convection signals will be relayed back from the in a vertical penetration that is open to a huge reservoir of fluid at temperature T plus delta T. Now we can move to the third problem. Look into it. This is a problem regarding the partially divided enclosures. So the figure shows a partially divided enclosure with a total height of h and Prandtl number greater than 1. So the thermal boundary layer thickness delta 1 is given by, so here h1 is the height of the first enclosure from the bottom, and h2 is the height of the bottom enclosure from the top. So the boundary layer thickness from the left wall will be hot. There will be two vertical sides, hot side and cold side, and the entire domain will not be participating in natural convection. There will be a trapped region on, as you could see from in the figure, on both the sides. There's a trapped hot fluid and there is a trapped cold fluid here. So that doesn't participate in the natural convection. So the natural convection circulation will be taking this route, and the boundary layer thickness on the first wall will be delta 1 and the second wall will be delta 2. We need to prove that the delta 1 is of the order of h1 RH Rayleigh number with respect to the total height raised to minus 1 by 4. So we actually need to check which out of these 4 is right. The new feature caused by the presence of a vertical obstacle inside the cavity. So these are the vertical obstacle. It is called this presents a new phenomenon called trapping of fluid on either side of this obstacle. So if this is the hot side and this is a cold side, the circulation will be like this, and the hot fluid will get trapped here and cold fluid somewhere here. Uh, so you could see the hot fluid get trapped in this side and cold fluid here. So here delta 1 will be the this dimension boundary layer, and delta 2 will be this dimension boundary layer for this side. H1 will be the vertical dimension scale for this boundary layer, because you could see the boundary layer goes into other domain at this particular point. So from the horizontal section to the top section, the height is h1, and similarly for the second wall, this section remains stationary. So this is a trapped section which remains uh, isolated from the circulation. So here the vertical length scale will be from starting from the ceiling, the roof, to the top edge of the obstruction from the bottom. So that will be the uh, scale for the in the vertical direction for the boundary layer on the right side. So we need to see how will the boundary layer be scaled as. So what will be the formula for the boundary layer? Delta 1 is of the order of which out of the four options? So is it h RH raised to minus 1 by 4, or h1 RH raised to minus 1 by 4, h minus h1 RH raised to minus 1 by 4, or h1 RH1 raised to minus 1 by 4? So what we could do is that we can start from the beginning for the uh, uh, natural convection. So we in the previous week's lecture, we have seen the scaling analysis for the natural convection, and we have identified the main terms that will remain in the energy equation as well as the momentum equation. So the scaling analysis of these two equations will give us the actual scale of the boundary layer in this case. So take the case of the left side boundary layer. So in this direction, h1 will be the height of the plate that will be in contact with the boundary layer, and the boundary layer dimension in scale in this direction is the boundary layer thickness delta 1. Uh, and so what we could assume is that the energy equation the main scaling analysis of the energy equation in the previous week, we saw that uh, this is x direction and this is y direction. It will be u dou t by dou x plus v dou t by dou y is equal to alpha dou square t divided by dou x square plus dou square t divided by dou y square. So out of that, we have seen that x scale will be very much smaller than that of the y. So x will remain, the other term will not remain. And the left hand side will be almost the same. So this can be scaled as u delta t divided by delta t, and this is v delta t divided by h1, and this will be alpha delta t divided by delta t squared. So we don't know the scale of v, so we make the use we make use of the continuity equation, and we scale it. Dou u by dou x plus dou v by dou y is equal to 0, and we will scale it as u by delta t is of the order of v by h. So we'll get v is of the order of so we'll get u is of the order of v delta t divided by h. Substituting it, what we'll be getting is that the left hand side, both the terms will be of the order of v delta t divided by h, and that will be of the order of alpha delta t divided by delta t squared on the right hand side. And solving these two, we get v is of the order of alpha h divided by delta t squared. So this will be equation 2. And then we move our attention to the momentum equation. The So take the case of uh, y momentum equation. It can be scaled as, so the momentum equation could be scaled as so in this case, both of these terms could be scaled as, this one will be u into v could be scaled as, this is uv divided by delta t, this is vv divided by delta t, this is h, and this could be scaled as u divided by nu v divided by delta t squared, nu v divided by x squared, and g beta delta t. So this is negligible. So only this persists. Similarly, this could be written as u could be written as v delta t divided by delta s. So the left hand side will be scaled as uh, v v squared divided by h. And right hand side nu v divided by delta t squared, and the buoyancy term will be g beta delta t. So this will be 3. So what we could see is that from 2 we could see the velocity could be scaled as alpha h divided by delta t squared. So we substituted here alpha h divided by delta t squared, alpha squared h squared divided by delta t squared h mu by delta t squared, and this will be alpha h divided by delta t g beta delta t. So canceling this will be alpha squared h divided by delta t squared mu alpha nu h divided by delta t cube and g beta delta t. And now we try to analyze between these three terms. The first term is the inertia term. Beg your pardon, this is alpha square, this is delta t raised to 4. Divided by, this will be delta t squared. So this will become delta t raised to 4. And so this is not h, it should be scaled as h1. So but there's a small correction, everything will become h1 here. So we are scaling for the left side boundary layer. So that will give us h1, h1. Okay. This will be the scaling analysis. This is the inertia term, this is the friction term, and this is the buoyancy term. We take the buoyancy term onto the left hand side. Alpha squared h1 divided by delta t raised to 4 into g beta delta t alpha nu h1 divided by delta t raised to 4 divided by g beta delta t, and this will be 1. So we can try to represent this in terms of Rayleigh number. Rayleigh number is represented as for with respect to h1, it is represented as g beta delta t h1 cube divided by mu alpha. We combine a few terms and do a bit of manipulation. So we need it in terms of Rayleigh number. So for this, it could be h1 cube. So h cube and mu alpha and mu alpha. Similarly, here it will be h1 cube, h raised to 4. Mu alpha is already there, so we need not do much here. So this will be Rayleigh number, and h and delta t you can combine together, club together, h by delta t into alpha. Alpha squared get cancelled, so it will be alpha by mu into 1 by Rayleigh number raised of h1. And here it will be h1 by delta t raised to 4 divided by Rayleigh number of h, and this will be 1. So this will be Prandtl number raised to -1. So you can write it as h by delta t raised to 4. Rayleigh number raised to -1, Prandtl number raised to -1 is of the order of h by delta t raised to 4, and Rayleigh number raised to -1 is of the order of 1. So what we could see is that in this particular problem, they have mentioned a height of total height of h with an individual height of these obstacles from the bottom h1 and from the top h2, and h1 plus h2 is greater than h, and Prandtl number is greater than 1. So we can assume Prandtl number to be significantly greater than 1. So we could say that this Prandtl number is significantly greater than 1. In that case, this particular term, when Prandtl number is very much greater than 1, this particular term will be very much less compared to the second term. So that means this approximately tend to 0, and in that case we could see is that h by delta t raised to 4 RAH with respect to the H1, RA H1, I beg your pardon, this is H1. I tend to mix between H and H1, so it is H1, make sure RH1 raised to -1 is of the order of 1. So that means that delta T is of the order of, take delta T on the other side, H1 raised to RA H1 raised to -1/4. So that solves the problem. So we got the order of delta T, that is also order of H1 RA H1 raised to -1/4. So that is option number 4. So this is the case of a partially divided enclosure for scaling and using a scaling analysis. We have arrived at the order of the boundary layer scale that is equal to when the Prandtl number is very much greater than 1, we could say that the second term, the viscous term dominates, and that will be uh, coupled with the buoyancy term since it's a natural conversion. So in that case, we could say that delta T is of the order of H1 or H1 raised to -1/4. So this is an overall analysis that is quite similar to the analysis that we have seen in the previous classes, and we just extend it. That's it. Look into the fourth problem. This is a theory problem uh, based on Bénard convection. We need to explain the phenomena of Bénard convection. When does this phenomena occurs, and what is the critical value of critical value at which this conversion occurs, Bénard convection occurs. A critical value of the Rayleigh number at which this conversion occurs. So, so the question says we need to explain what is the phenomenon of Bernard convection. So, this is completely different from different kind of a convection than what we had seen till now. Normally, in the case of vertical walls, and we consider two vertical walls, and one at a hot temperature T hot and other two cold. So, as and when there is a temperature difference, you could experience circulation, natural convection circulation straight away. But when the walls are horizontal, that is separated by a distance h, the bottom at th and top at tc, there is you can't expect the natural conversion to set in straight away. There is a finite value of the critical value of the Rayleigh number that is calculated with respect to the distance, the gap between the two walls, above which the natural convection sets in. So when the Rayleigh number is less than the critical value of the Rayleigh number, the you could see Nusselt number with respect to scale with respect to x is of the order of 1. So that means that there is no convection at all. It is basically conduction that is thermally stratified. Fluid. But when the Rayleigh number is greater than the critical Rayleigh number, first presence of natural convection sets in. These are the flow consists of counteracting two-dimensional rolls, and these are called as Bernard cells or Bernard convection. So once the Rayleigh number is above the critical value of the Rayleigh number, the convection sets in. And this is counteracting in the sense the adjacent ones will be same as that of the previous one. So this one goes like this. The adjacent one will be like this. So these cells are called Bernard cells or Bernard conversion. So this when a plate is heated from the bottom, when a plate is heated from the bottom and it is an enclosure or which is sufficiently long in the other direction, two directions, and separated by h above the value of critical Rayleigh number, counteracting uh, 2D roll sets in setting, and this is called this flow pattern is called the Bernard cells, and the flow is called the Bernard convection. And he had experimentally, the scientists named This Bernard cells or Bernard convection is named after H. Bernard, the scientist who discovered this phenomenon, and he found out that this critical Reynolds number uh, equal to for two walls separated by a distance h is equal to 1708, should be greater than or equal to 1708. Critical Reynolds number is equal to 1708. And here, in this case, when the Nusselt number, when the Rayleigh number is greater than the critical Rayleigh number, natural conversion sets in, and the Nusselt number is greater than 1. So that explains the phenomenon of the Bernard convection. So we look into the first problem. This is also a theory problem. So this question asks, how does the inclination of the enclosure affect the heat flow characteristics? So as you could see, the enclosures in all our cases, we have considered it to be the vertical or horizontal. So how does it vary with respect to an angle? We have looked into an extreme two cases. Now we need to look how does it vary for different angles in between. So basically in this case, we need to consider the angle of inclination. So a Nusselt number of 1 corresponds to a case where conduction dominates over convection. That means that there is no effect of convection. So that corresponds to a thermally stratified flow. For example, when it is heated from the top. So if you consider an enclosure, we consider two extreme cases of cold, hot. So we consider two extreme cases. So the hot surface is at the bottom, cold at top, and we could consider this to be at an angle of 0. So theta equal to 0. And when the hot surface and cold surface are vertical, that angle will be 90. And when the hot surface will be on top of the cold surface, the angle will be 180 degree. So these are two extreme cases. So here there will be a thermally stratified flow, conduction. So Nusselt number will be approximately 1. And if this Rayleigh number is greater than the critical Rayleigh number that we have seen for the case of Bernard cells, we could see that Nusselt number will be greater than 1. So there will be the cellular convection. So there will be cellular convection. So the here the Nusselt number will be greater than 1. So if you draw a Nusselt number versus angle of inclination theta at 180 degree, the value will be equal to 1, and at 0 degree, the value will be somewhere high. So we do not know what happens in between. So this is Bernard convection. What we have seen in the previous case. So what happens is that the Nusselt number value, the heat transfer, as well as the natural convection varies as and when the orientation changes. So what we do is that we tilt this cold, hot, and this is theta. So this is actually Bernard convection, and this is minimum. So what we could see is that when the theta increases and becomes vertical, this will be a hot wall and this will be a cold. This will be the normal natural convection case where the circulation happens from cold to hot. So we could say that when we tilt when we tilt the enclosure from 180 degree to 90 degree from this orientation to a vertical orientation, Nusselt number increases. But again, when it goes below, and when it reaches the 90 degree, you can expect a maxima because hot wall is on the left and cold wall is on the right, and the gravity, there is gravity buoyancy will be completely assisting the natural convection in this case. So in this case, the angle will be 90 degree and you can expect a maximum. As and when we tilt it back to 0 degrees Celsius, you could see a drop and it reaches a particular critical angle theta star, from where it goes back to the theta equal to 0, that is the Bernard convection case. So as you could see from the figure of the Nusselt number variation with respect to the orientation, angle of inclination, theta equal to 0 when the hot wall is at bottom, cold wall is at the top. We can expect a Bernard convection when the Rayleigh number is greater than the critical Rayleigh number. Then if that critical Rayleigh number, if the Rayleigh number was less than the critical Rayleigh number, then this would have followed identical. This would have been identical compared to that of this section of the graph would have been identical as that of the left hand side. But if the Rayleigh number is greater than this one, then we could expect Bernard convection, and there is a maxima, local maxima corresponding to the Bernard convection. If it was not there, the maximum would have been at theta equal to 90 degree. When the vertical walls will be parallel to each other. The enclosures, both the sides of the walls will be parallel to each other. So this is how the inclination of an enclosure, affected the flow characteristic for Nusselt number, for the Nusselt number in the case of natural convection. Look into the sixth problem. This is a problem associated with the turbulent flow. Uh, this is the case of a turbulent flow, but it's a transition. It actually doesn't deal with the turbulence as well. This is a starting to the turbulence. So this is a scaling analysis, kind of a scaling analysis problem. We have to show that the transition condition listed for boundary layer flow in this table correspond to a critical Reynolds number of order 10 power 2 if the critical Reynolds number is based on either displacement or momentum thickness of the boundary layer. So for that, we need to know what is the displacement thickness and the boundary layer, displacement thickness for a flow or a flat plate, as well as the momentum thickness. So the Rayleigh number, the most conservative of the estimate shows that the Rayleigh number should be less than 2 into 10 power 4 for the lambda case, and above that it will be turbulent. So Rayleigh number with respect to L equal to U L divided by U infinity L divided by mu, that is equal to 2 into 10 power 4. So so we have this given information. So we'll take this, that is the most conservative value. It's a flow over a flat plate case. So forget about this one, which is only the first case. And in that case, we need to show the Rayleigh number with the Reynolds number that is determined with respect to the displacement thickness delta star. Reynolds number that is calculated with respect to displacement thickness is equal to u infinity delta star divided by mu, that is u infinity L divided by mu into delta star divided by L, that is REL into delta star divided by M. Similarly, the Reynolds number with respect to momentum thickness, theta star is given as RE theta star equal to u infinity theta star divided by mu, could be written as REL is to theta star divided by L. So if we know the value of this delta star divided by L, we can directly calculate the value of the Reynolds number, and for the momentum thickness also we can. So as we could see in the case of earlier analysis, we have calculated the value of the displacement thickness as well as the momentum thickness. So the displacement thickness delta star divided by L could be written as 1.3 into Rayleigh number raised to 1 by 2. This will be of the same order as that of the boundary layer thickness. So boundary layer thickness, we could see 4.9 divided by root of Reynolds number. See, this is also similar, but of the same order, but the constants will vary. And in the case of momentum thickness, this is quite similar to that of the shear stress that we have seen. So here it will be theta star divided by L will be have the same constant as that of the shear stress, 0.664 divided by REL raised to 1 by 2. So substituting the value of Rayleigh number raised to L, you can get a value of REL raised to minus 1 by 2, and this is fine. Okay. That implies Reynolds number with respect to the displacement thickness will be 1.73 into Rayleigh number raised to 1 by 2. And similarly, Reynolds number with respect to the momentum thickness will be equal to 0.664 raised to Reynolds number raised to 1 by 2. That's equal to, so this is equal to 245 and this is equal to 94. So this shows this is of the order of 10 square, approximately equal to the 10 square. So order of hundreds. This will be 94 will be it's approximately 100, and similarly this also will be or approximately to 100. So both of them will be order of 100. So that solves the problem, and that's completes the problem set that I had for this week. So in this week, we have seen few theoretical questions and multiple choice question based on internal natural convection, scaling analysis of a few of them, partially divided enclosure, inclined enclosure, and one question based on the turbulence. So this is based on the lecture series of the 9th week that was uploaded in the NPTEL website of Convective Heat and Mass Transfer. So if you have any doubts, you can post them in the course forum. We will try to solve it. That's all for the week. we'll meet again the next week. In the so if you have any questions, you can also mention that, or I'll also try to clarify it in the upcoming session. Thank you.